So we'll continue with the first session of the three-part tutorial given by Dima Sinapova on the tree property.
I would like to thank the organizers for this invitation. It's a great pleasure to be here. And so I'm going to be talking about the tree property, and the plan for this three-part session is as follows. So I'm going to start with just some historical background and the classical results we know about. And so one of the main motivations behind this topic is the following kind of an old project in set theory, which is the question, can we consistently get the tree property at every regular cardinal greater than ℵ1? So can we get the tree property at every regular kappa greater than ℵ1? And so I'm going to start with an overview of some past results. Then I want to talk about a recent result which says that starting from ℵ many supercompact cardinals, one can consistently get the tree property at the first and second successor of a singular strong limit. So from ℵ many supercompact cardinals, it is consistent to get the tree property at kappa plus and kappa double plus, where kappa is a singular strong limit. And then, depending on how much time we have, probably the last day, I will be talking about pushing some of these results down and partial progress on it to smaller cardinals, so accessible cardinals. And the last part of the tutorial will mostly be about results that are joined with Spencer-Unger. Okay, so what is the tree property? Let me start with a definition. And I'll be abbreviating it TP at kappa. So TP at kappa says that every tree of height kappa with levels of size strictly less than kappa has a cofinal branch. Okay, so this combinatorial principle is a compactness type principle, which says that, well, if you have a tree that's height kappa, but not too wide, just like for any level alpha less than kappa, you can certainly walk up to that level. Well, there should be a cofinal branch through the whole tree. So this is an instance of compactness type combinatorial principle. Okay. And as such, it's not too surprising that it also, in a way, it characterizes large cardinals, so it's a remnant of large cardinals, and actually it really captures what it's so if kappa is inaccessible and has the tree property, that happens if and only if it's weakly compact. So it captures the essence of, for example, weak compactness. For now, let me just say it is, so we can view it as a remnant of large cardinals, but it's a remnant of large cardinals that can actually hold at successor cardinals, but can actually hold consistently. Successor cardinals. And okay, so let me start with a very first sketch, a picture why, for example, kappa measurable implies the tree property at kappa holds. Okay, so. And this will also illustrate the compactness typeness of this combinatorial principle. So, for example, if kappa is measurable, then kappa has the tree property. And okay, so how do we show this? Well, let's take a tree of height kappa. And since kappa is measurable, well, we do the only thing we can do with this tree, hit it with an elementary embedding. So suppose we have some j, and one can look at j of t. So j of t, where j is, with critical point kappa, is a tree of height j of kappa. In particular, one of its levels is at kappa, so we can take a node u on of the tree j of t at level kappa. And now, since this is a tree, we can trace all of u's predecessors. Let's call this b. And b can actually be pulled back through j, yielding a branch through t. So now, pulling it back, we get a branch through t. Okay, and okay, so we know we can get the tree property for large cardinals. Well, but as I mentioned, it can hold at successor cardinals. So let me go over what's known about that. Well, so first, this is not a successor cardinal, but by Koenig's infinity lemma, well, we certainly know that the tree property holds at omega. Well, what about at omega 1? Again, that's a classical result that there is an Arrangian tree, so the tree property fails at omega 1. And then the first consistency result was by Mitchell, who in 72 showed that starting from a weak compact cardinal, one can build a model where the tree property holds at L of 2. So it's consistent to get the TP at L of 2 from a weakly compact cardinal. Okay, and this is when, I believe, I wasn't around then, I think this is when a bunch of people, Magidar and others, asked, okay, well, we can get it at omega 2. Large cardinals are powerful, we can do everything with them. Can we possibly get it at, every regular cardinal? And people started looking. And about 10 years later, Abraham, so 80, that was Reagan administration, 83, showed that, what? Okay, yeah, because they were together, right? She won, and then finally Abraham showed that we can get TP at L2 and L3 for simultaneously. Now, his large cardinal hypothesis, which was much stronger, so this is from a super compact and a weakly compact above it. So in my notation, when I say SC, that will be always super compact. Cardinal plus weakly compact above it. Okay. So what was the next important result? This came in 98. It's published in 98 by Cummings and Foreman. Who showed that starting from omega many supercompact cardinals, one can get the tree property at all of the alphans for n greater than 2. So it's consistent to get TP at alphan for all n greater than or equal to 2. And this is from omega many supercompact cardinals. All right, so it's been a kind of, as you can see, 10 years and more slow but steady progress. And then the next, one of the next key results is by Neeman. So this happened in, I think he did it in 2012, published in 2014, I believe, that the result by Cummings and Foreman can actually be extended to add alpha omega plus 1. So he showed that it is consistent to get the tree property for every alphan n greater than or equal to 2, together with TP at alpha omega plus 1. And this is again from omega many supercompact cardinals. And so one of the next questions, which is
you don't need anything above the omega supercompact?
actually no. So I'm gonna talk a little bit about this more in detail, but the first proof that the tree property can be consistently obtained at alpha omega plus 1 was due to Magidor-Shalai, and for that they used the huge cardinal and omega many supercompact cardinals. But actually, at some point I noticed that you can get the tree property at alpha omega plus 1 just with omega many supercompact cardinals. And I believe Itai used that as partly for his motivation together with the model of Cummings-Foreman. But so no, it's just omega many supercompact cardinals. And so since we're talking about the aleph, let me say that it's still open whether one can get a situation where, so alpha omega strong limit and the tree property at alpha omega plus 1 together with the tree property at alpha omega plus 2. Now, if one drops the requirement for alpha omega to be strong limit, then it is known, so there is a result by Cy Friedman and Laura Fontanello that the tree property can be achieved at alpha omega plus 1 and alpha omega plus 2, but there alpha omega is not strong limit, and in particular SCH holds at alpha omega. In this case, I mean, that's still open, but so one partial progress result that I'll be talking about a little later is that at least it can be done for some cardinal high up. So now, since
What is the cofinality of that couple?
omega. Now, why does it make a difference? Since I started saying something about it for strong limit. Well, Specker showed, actually generalizing really the proof that there exists an arrangement tree, no, just a vanilla arrangement tree at omega 1, is that we have, this was, something 1 maybe? That if kappa to the less than kappa equals kappa, then we have that the tree property holds at kappa. No, kappa plus. No, this was supposed to be kappa minus. Yeah. Kappa plus, of course. So, for example, what? Oh, fails. Yeah, so you can get an arrangement tree at kappa plus. Moreover, I mean, I want the tree property to hold so badly everywhere. And if you are in this situation, you can actually construct a special arrangement tree. So one consequence of this is that if alpha omega is strong limit, and if you want to achieve the tree property at alpha omega plus 2, then you need to violate SCH at alpha omega. So to get the tree property at alpha omega plus 2, we need SCH to fail at alpha omega. Otherwise, by Specker's result, there is a arrangement tree. So, okay, well, if we're trying to get, that's why it matters when alpha omega is strong limit. So if we're trying to, approach this open question, well, let's go and see what the situation of SCH is here. Well, actually, it turns out in both of these models, SCH does hold. Okay, but in this theorem, the one I'm going to talk about here SCH at kappa will fail. Okay. Oh, also, I should have mentioned this a little earlier. That's again like a note. Consequence of Specker's result is, for example, the continuum hypothesis implies that the tree property will fail at omega 2. So that's why one can just say, well, let's take a measurable and Levy collapse it to omega 2. Will we still have the tree property? Well, the answer is no. So what in Mitchell's forcing, for instance, so it starts with a weakly compact, and the size of the reals is blown up, so the SCH fails, as it should. Okay. All right. Okay. So the next thing I want to talk about is
what about the tree property just at aleph omega plus 2? You said it's open to have both at aleph omega plus 1 and aleph omega plus 2. Can you get that at just aleph omega plus 2?
Yeah, so it is consistent to get the tree property at aleph omega plus 2, and I think there are several ways one can do it. So this is due to results by Cy Friedman. There is also a paper by Moti Gitti, and actually let me send some notes. So we know that it is consistent to get TP at alpha omega plus 2, but I mean, I'm probably forgetting someone. I mean, this is independently. So different constructions. So Moti did it with extender-based forcing, Sayan and Halilovic. Use Sachs forcing, and of course there is, let me write it. If we drop the requirement for alpha omega being strong limit, then you can actually get tree property at both of these. So this was done by Laura and Sai. Can get. And this is a recent paper. Okay, but so the one common feature of all of these models is that weak square holds at alpha omega there. So in all of these, weak square at alpha omega holds. And actually, so among other things, this implies that the tree property at alpha omega plus 1 will fail. And so we don't have, it's not really very optimistic to try to get this construction, modify these constructions to get the tree property at both. All right. Okay, and any other questions about some of the background of what's out literature? All right. Okay, so I've been talking about first and double successor of a singular. Well, let me now focus on the topic of just how does one obtain the tree property at successor of a singular to begin with. So tree property of successor, a successor of a singular. Okay, so going back to just theorems of ZFC, we know that like if we start with large cardinal, say for example kappa measurable, we get the tree property at kappa. Well, what kind of large cardinals do we need to get the tree property at successors of singulars? And the first key theorem here was by Magidor-Shelah. I believe published in '96, maybe a little earlier, the actual proof, that if we have an increasing sequence, kappa n less than omega, of supercompact cardinals, increasing supercompact cardinals, then the tree property holds at the successor of their supremum. So let's set mu, let mu be sub kappa n plus, okay? Then, so this is just a theorem of ZFC, as you know, some mathematicians do work in ZFC, holds at, mu. And let me just draw two pictures which, illustrate like the key ideas of the proof. So why? I say proof, but I use this loosely. Well, so let's start with supercompact cardinals kappa n, and let T be a mu tree. So what does that mean? The height is mu. Now levels are of size less than the supremum. Let me give this a name. Let kappa be the sub of the kappa n's. And we may as well assume that for all alpha less than mu, so for every level on the tree, that the alphath level, T alpha, has nodes indexed by singleton alpha times kappa. Okay. And so the structure of the tree is, of course, which nodes are comparable. So the proof goes in 2 stages. So stage 1, maybe I should do it over there. So stage 1 is to use the supercompactness of the first cardinal, kappa 0, to narrow down the tree a little bit, namely to show that one can restrict oneself to like a subsystem of this tree whose levels are of size less than some kappa n. Okay, now stage 1. Is to show that there is some natural number n and some unbounded subset I of the levels of T, such that on any 2 levels from I, you can find nodes that are comparable whose index is only up to kappa n. More precisely, such that for every alpha beta in I, say alpha less than beta, there exists some psi and delta less than kappa n, such that alpha psi is less than beta delta. So how does one do that? Well, okay, so again, there's really one thing we can do. So we have T J of T and well, okay. So here the height is mu, the height will be J of mu. The critical point of J is kappa 0, and we want to pick a node U on the right level of J of T. So J of T has height J of mu, but somewhere here is sub J image mu. So we want to pick a node, or just even a node on this level, yeah, and trace it down. And now, looking at all of its predecessors, I mean, each of them are indexed by some psi less than some kappa n, and on an unbounded set, I mean, I don't want to write too much, I want to leave it as a picture, but one can find some I, some unbounded set of those levels, such that for every alpha in I, there exists psi less than J of kappa n, such that alpha psi is less than U. And then use elementarity to show that such an I exists when we talk about the actual tree. Okay, so now use
There
it.
exists such an n, or
Yeah, we find I and n such that, so one looks at every predecessor of this node. So for every here alpha, I should say J of alpha here, looks at every predecessor, and I know that such a psi exists less than J of kappa, so it would be less than one of the J of kappa n's. And then pigeonhole principle, those n's must be constant on an unbounded set. Let me pull it back. Okay. Now, of course, you cannot actually hope to pull back this branch as is, because now the critical point here is kappa 0. And then once we have this n, stage 2, that's when we use the supercompactness of I guess, kappa n plus 1 to define our branch. And then the picture is, now we have our tree, T, we hit it, so again, level mu, kappa n plus 1. We hit it with the elementary embedding of critical point kappa n plus 1, which witnesses the mu supercompactness of kappa n plus 1. So if this is J of mu, again, here we have sub J image mu, J of kappa n plus 1 is somewhere here. And now I look at J of I, where I was fixed in the first stage. Well, this is an unbounded subset of J of mu, so we fix a point gamma, so we fix a point gamma here, a level gamma in J of I. And then again, using, I think, the pigeonhole principle twice, we end up getting a null dual such that now its predecessors can be pushed back to give a branch.
The way you present this proof looks like you could just use a measurable. Can you please tell us?
Okay, well, it's important that at one point, some of the argument happens in M, and it's important that M is closed under mu sequences, where mu is the supremum of the cardinal. Okay. So it's, I mean, you are using the supercompactness. Any other questions? I mean, I can be more detailed, but that will be detailed later. Okay.
So strong compactness is enough.
Hmm?
Strong
Yes, I should. Yeah, I should say. So actually, yes, strong compactness is enough. I decided to present this for in the assuming supercompactness because this relates to what I'll be doing later, and it's gives a chance to illustrate this with elementary embeddings. But Moti is right. One can just use the strong compact filters and run a similar argument. Okay. So yeah, in the original paper, the proof is with strong compactness. Okay. So I guess in this one case, SC can also stand for strong compact. Any other questions? Okay. Let's see. All right. So this is, about the tree property at successors of singulars for what we know as a theorem of CFC. So now, again, going back to this, where is it? Fact of life over there, that if one wants to attempt to get it for both kappa plus and kappa double plus, where kappa is strong limit, well, we need to violate SCH at kappa. So that had been kind of an odd question. Well, can one get, something like this, the tree property at successor of a singular with failure of SCH at kappa? So, for example, in this situation, SCH at kappa certainly holds. And then, in some years back, this will actually be appropriate to this status under this theorem. So I showed that, well, consistently, yeah, actually it is possible to get the tree property at kappa plus together at failure of SCH at kappa. Starting from, again, from omega, many supercompacts. Can get the tree property at kappa plus and failure of SCH at kappa. So as we all know, in order to violate SCH at kappa, people usually have to rely on Prikry forcing. So what we used is diagonal supercompact Prikry forcing. I'm gonna talk, give like a brief outline in a second, but let me say, so this type of forcing, diagonal supercompact Prikry forcing, first appeared, so this is from a paper by Moti and Asaf Sharon from 07, from Gittik. Sharon. So since the exact conclusion that is, so the exact way that Itai gets the tree property in this model actually is key ingredient in the proof that we can get it at both kappa plus and kappa double plus, I will do just kind of like a itemize some of the key points of this construction. Okay. So what are the key points? Well, is to somehow interleave the situation of Magidor-Shala with a diagonal supercompact Prikry forcing. Okay, so what does he do? Well, again, start with, just like in the Magidor-Shala case. Now let me call kappa to be kappa 0, again, kappa n. Let nu be the supremum of the kappa n's. And again, let mu be the successor. So, same situation as in the Magidor-Shala theorem. But now, what we want to do is blow up the power set of kappa, because SCH needs to be violated, and then singularize this interval of cardinals using the diagonal Prikry forcing from Gittik-Sharon. In a nutshell, so V here, all the kappa n's are supercompact. Kappa 0 is indestructibly supercompact. The first stage is blowing up the power set. So this is add kappa mu plus. So mu is destined to become the successor of kappa 0. Okay, so now here mu 2 to the kappa is over here. And again, kappa is still supercompact. Now the kappa n's, when they remain cardinals, they're no longer supercompact, but they used to be. So the argument involves lifting embeddings at some point, and then force with the Prikry. So V, that's add, and let me call the Prikry by P, where the cofinality of kappa becomes omega, mu will become kappa plus, and the power set of kappa is mu plus. So SCH at kappa is violated because kappa is a singular strong limit with big power set. These guys are all, every kappa n is singularized to have cofinality omega, so in particular it is collapsed to kappa. And kappa itself remains a cardinal. So this P, this supercompact Prikry forcing, so it's diagonal supercompact Prikry forcing, which uses omega many normal measures. So let me tell you what those are. So in here we fix un for n greater than omega normal measures on p kappa n, and p adds a generic sequence, a Prikry generic sequence xn n less than omega, such that each xn is in p kappa kappa n, and their union is nu, where nu was the supremum of the cardinals. So, nice density argument shows that this sequence witnesses that one has singularized every kappa n. Okay. And when I said that this forcing first appeared in Gittig-Sharon, so in their setup, kappa n was just kappa plus n, so the n successor of kappa. So what their theorem is, let me write it, is that consistently one can get failure of SCH at kappa and failure of weak squared kappa, actually failure of the approachability property, but since I don't want to define that, failure of weak squared kappa, among other things. They also got other things, but this is one. Okay. So then the next big, like the key point in its proof, okay, so we have this, well, at one point in life, the tree property did hold at mu. Let's show that it still holds after doing Otis forcing. And surprisingly, the proof that the tree property holds in that last model is, if one wants to take a simplistic approach, it kind of follows Magidor-Shalat, but on a lot of speed, say. So let's let me say a few things about this. So before I do, I want to actually give a definition of this Prikry forcing P. So conditions in P, in this intermediate model, and I'm missing a parenthesis, bracket. In this intermediate model, we fix those normal measures un on p kappa kappa n. And conditions are of the form, so we have the stem x0, x1, dot, 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 xn minus 1, and then some measure 1 sets, an plus 1, etc., where each measure 1 set ai is from the normal measure ui. Each Prikry point, say xl, is in p kappa kappa l, where the little x's are so they're called the stem of p. This is what I'll refer to as the stem of P, and this is what P decides is the initial segment of the generic Prikry sequence. Those x's are increasing in the sense that, so XL is backslash Prek increasing XL plus 1, which means that one is a subset of the other, and the order type of XL is strictly less than kappa intersection, and this is an inaccessible cardinal. Well, let me write it like that, of the next Prikry point. So this is called the stem of P. Okay, so now how do we, how does it show the Prikry property in the final model? Well, since one would like to kind of use ideas from the Magidor-Shalat argument, well, that means we have to work in V at. So to get
Then you wrote the XL belongs to what? Cannot see.
P kappa kappa L. So these are the, so this is a kappa.
I understand.
Yeah. And of course, so these measure 1 sets are the ways a certain given condition can be extended. So to extend P, I have to increase, say if I want to increase the stem, I have to pick points from the measure 1 sets. So to get the tree property at mu. So key point is we want to work in that intermediate model, in V at. Okay. Because only there one has some elementary embeddings or can lift elementary embeddings. It's actually, you cannot do that if you go all the way to the Prikry model. I'll work in V at, and with, well, since we don't have the tree, we do the next best thing, and this is take a name for the tree. So fix T dot, a name for a mu tree, Prikry name for a mu tree in the final model. And again, we may assume that the alpha level is actually indexed by alpha cross kappa. So the nodes do exist in every model we want. Of course, the ordering is where we only have a name for. Okay. And again, it's stage, what did I say here? Stage 1, there is an n. Well, something very similar happens in this proof. So let me call this lemma 1. Is that one can fix an unbounded subset I, just like in here, such that for every alpha and beta in I, one can find, here it will be kappa, but one can find points psi delta less than kappa, such that this thing is forced by a condition of whose stem has length n. Okay, so let me write this, and you see how actually kind of nicely parallels this case. So lemma 1 is there is an unbounded subset I and some natural number n, such that for every alpha beta taken from I, well, alpha less than beta, there is, or there are, I should say, psi delta less than kappa and a condition P with length n, and the length of a condition is the length of the stem. So for example, here P has length n. Condition with length n such that, P forces alpha psi less than beta delta.
So, do you really want to assume that the alpha equals the product, or just it is a constant?
You can actually assume it equals it.
Actually, is this kappa? It's not kappa 0.
Yeah, in this case, I decided kappa to be kappa 0.
So this kappa is kappa 0?
This kappa is kappa 0, yeah. Okay, yeah, this kappa is not that kappa, but this kappa is kappa 0. Okay. Oh, you're asking why are the levels kappa 0? Well, know that kappa is the predecessor of mu here. So since all of these cardinals are collapsed to kappa, we may as well assume that the levels are indexed by kappa, the predecessor of mu in the final model. Okay, so now what does the proof of this lemma use as well? Similar to this case, the proof uses two key points. Uses a mu supercompact embedding J from V add with critical point kappa, or kappa 0, just like over there. And so recall that in V one takes the kappa ends to be supercompact, indestructibly supercompact. So since the cone poset is closed enough, in V at kappa mu plus kappa is still supercompact, we can actually take an embedding. And then the argument proceeds almost as this one with one tweak, and that tweak is that since we're talking, you know, about conditions in the Prikry forcing deciding a comparability of nodes, the argument uses that J of P preserves, it's kind of a technical point, but I want to mention it for people who are more familiar with this stuff, preserves mu. So in order to use the pigeonhole principle on the J side, one has to use the J of P preserves mu. Otherwise, it's, you know, very similar to what happened here. And erase this. So this is fixing the length of a condition. Well, so the next step, which kind of parallels this stage 2, is fixing the stance. So a very similar statement as in lemma 1, but not only you're fixing the length, you're actually fixing the stem of such a condition. So in other words, this says that there is an unbounded set of levels of this tree, so J subset of mu, such that there is also a stem. So this is some, as above, some finite sequence of Prikry points, stem H, and some index. We can actually even fix the index here, xi less than kappa, such that for every alpha beta in J with, say, alpha less than beta, there is a condition P with stem H which decides that alpha xi is less than beta xi. With stem H such that P forces alpha xi less than T beta xi. Okay, and similarly to what's used here in stage 2, this lemma 2, the proof uses the supercompactness of kappa n plus 1. I need to go 1 up. So of course now kappa n plus 1 is no longer a supercompact in the model that we're working in. So we're working in V at. So we have to lift the embedding.
Sorry, is it the same size?
You can actually make it the same psi, yes. I think in your original paper it says psi alpha, but yeah. Just by the pigeonhole principle, by thinking it out. So I'm not going to write anything more about the proof, but I'm just going to say, what does one do? I mean, just like in here, going back to the original model V where everybody is super compact, take a mu super compact embedding with a critical point kappa n plus 1. Then lift this embedding over the model V add. And do some work, some reflection type arguments similar to these guys to find what we want to find, J and stem H, again by working on the J side, picking the appropriate node, reflecting the branch. And then we're almost done, except that since we have to lift the embedding, first we end up first Itai ends up finding this J in like an outer model, V add and then J of add, the uppercase J. And so then there is a kind of a tricky yet pleasant argument that if such an unbounded set exists in an outer model, by absoluteness one can show that it exists in the model where we want it to. So I mean the argument is quite more involved than this one, but. No, morally tries to follow it. Okay, and then, so now fixing the length, fixing the stem, what's next? Then there is a argument that one can, once you fix the stem, build a property measure one set, and at the end of the day, the following, finally, after a bunch of other claims and lemmas, one gets the following, and this will be crucial in, ends up being crucial in then extending the result to the double successor. So I want to write this. Get an unbounded, again working in V, add an unbounded uppercase J mu by, I mean, one will have to actually thin out this guy, but it's a subset. I'll use the same letter. Now, psi and a stem H. This will be the same stem H. And a sequence P alpha taken from J of Prikry conditions such that every P alpha has a stem H and for all alpha less than beta both taken from J, we have that P alpha, if you take the weakest common extension of P alpha and P beta, which always exists because conditions of the same stem always have a common extension simply by intersecting their measure one sets, that these forces alpha psi is less than P beta psi. So this is almost a branch. I mean, we have a bunch of nodes, so the nodes are alpha psi for alpha in J, unboundedly many nodes, and unboundedly many conditions such that for any two alphas and beta, P alpha meet P beta forces that those two are connected, comparable. And now finally, using the fact that this Prikry poset P has the mu chain condition, one can show that for unboundedly many alpha, those guys are elements of the generic poset. So by mu cc of the Prikry poset P alpha such that P alpha is in the generic for the Prikry, let me call this G sub P, is unbounded. And so this gives us a branch. The branch is alpha comma psi for alpha in this set. Let me call this J star. And so, okay. And so alpha psi such that alpha is in J star is a branch, cofinal branch. And I want to make one more note, remark here, and then I'll pull out the board, that each P alpha, let me call this B, each P alpha forces that alpha psi is in the branch B. Okay. So this is, like the final conclusion of getting the tree property. Not only do we get the tree property, but we get it in a very explicit way. So we get this set of nodes and a set of conditions such that each one of them, each P alpha forces the node U alpha is in the branch, and by the chain condition, unboundedly many of them are actually in the generic object. So, okay, so since I only have like 1 minute, let me just say what is, so what does one do to extend this to kappa double plus, and I'll be more specific tomorrow. But the idea is to take Mitchell's forcing to get the tree property at omega 2 and plug in the eta is Prikry forcing. I mean, that's basically it. So the idea is to get, okay, so this is my kappa 0. This is mu. This is, oh, I do need a weakly compact lambda. So what does Mitchell forcing do? Mitchell forcing, if you think of kappa standing for omega, Mitchell's forcing does blow up the power set of kappa to lambda, makes mu kappa plus by preserves mu and sorry, makes lambda mu plus by collapsing all of these cardinals to mu. So if you think of the Mitchell's poset where now kappa is omega and this mu stands for, say, omega 1. So what do we want to do here? Well, here we want to start with the same setup as in Ito's theorem. So kappa, and mu is the supremum of the kappa n plus. And we have this lambda here, which is some weakly compact. So we want to do several, we have several tasks to do. So to do, well, first make 2 to the kappa be lambda, make mu equal kappa plus, make kappa singular, and get the tree property at lambda, or ensure that it still holds, and the tree property at mu. So this, and this are basically taking Mitchell's original poset, but with modifications, well, kind of important modifications, by interleaving a diagonal Prikry in it. And so this result is motivated, has appeared in the past, for example, in Cummings-Forman, that paper in late 90s, and then Spencer-Unger plugged in Gittig-Sharon's diagonal Prikry forcing into this, and for this result, we're just plugging in Ito's version of the Gittig-Sharon forcing within the Mitchell poset. So basically, everybody who's kind of thought about this just for a little bit knows that this is the model, but the interesting thing is how one ensures that the tree property is still preserved. And this is what I'll talk about next time.
Okay, I'm afraid there's no time for questions. Just a reminder that there's been a change in the contributed talk schedule. It's now been updated on the web page, but so the change is the following. Alexander Błaszczyk will speak here in this room at 2 o'clock, and Caroline Antos will speak in room number 2 in the next building, also at 2 o'clock.